Okay, once you have your data, your emission spectrum, then you're ready to proceed with the analysis. And it's a little bit tricky. I mean, it's both straightforward and confusing at the same time. So let's just go over a few points before you do your work. Okay, so I assume that your results look something like this. They consist of a series of absorption lines, of emission lines, um, in a spectrum, okay? And you should probably see a set of sharp emission lines. You may see some other broad features at lower intensities. And these might be artifacts due to contamination of the gas in the tubes. You could prove that by doing measurements on many different tubes and looking for the common features. Those must be hydrogen. Whereas contamination would vary from tube to tube. But let's say we've done that and we've identified the features that we want to that we are associating with hydrogen and we want to analyze. Okay? So as I mentioned, one issue is that we don't know what the initial state and final state is for any of these lines a priori, because the lines don't come with labels. So let's make a couple assumptions, and we'll get to test those assumptions through our analysis. First, let's assume that all the lines come from the same series. Where by series, I mean exactly what's described here. So there's the Lyman series, the Balmer series, the Paschen series, and so on. So what this really means is that they all share the same final state. The final state is the same for all, okay? Of course, we still don't know what that is, but you can imagine that it's either 1 or 2 or 3 or some other number, okay? And we can figure out what it is when we analyze the data. The second thing we'll assume is that there are no missing lines. And what that means is that all the lines we see have initial states that are equal to, well, there should be one line corresponding to NF plus 1. That would be like this transition. If NF were 1, let's say, then one line would be N from NF plus 1, or N equals 2, down to N equals 1. And the next line would be NF plus 2, and the next line would be NF plus 3, and so on. But we're not missing any lines in this series. In other words, all the lines we see, we're assuming for the moment, come from the same series, and we're not missing any lines in the series. That's a good place to start. Okay? Here, let's pause for a second. Oh, here's a suggestion based on what we've just said. It's convenient to give our lines labels. Maybe we'll label them lambda 1, lambda 2, lambda 3, and so on, where this is just a number, 1, 2, 3, which doesn't necessarily equal the initial state number or the final state number or anything. It's just a way of keeping track of the lines. But we might like to at least have the order of the lines be the same as the order of the initial states. You know what I mean? In other words, that let's say again that the final state were 1, that this would be line number 1, 2, 3, and so on. Okay? It's helpful if they're in the right order anyway. How can we do that? How can we make sure we have the order right? Well, just notice in this drawing for each series, the line that's furthest to the left is at the lowest energy. That means it should be at the longest wavelength. And so we can assure the ordering will be right if we start our ordering, if we label the first line as the line of longest wavelength, and then label them in succession to shorter and shorter wavelength. So lambda 1, lambda 2, lambda 3, and so on, just as I've indicated here. At least that'll keep them in the right order. Okay? Very good. Let's stop here.